All right, hello everybody. Welcome back to another round of Statistics for Linguists. We're going to talk today about logistic regression. I think we don't really need a whole lot of preamble for this because I gave it to you at the end of the last lecture, so why don't we just get on into it. The way we're going to start the lecture out today is by talking about not probability, but odds, which are closely related to probability. So it might help to go back a bit to our Dungeons and Dragons days, although I don't think I'm going to talk about Dungeons and Dragons specifically today, be that as it may. Anyways, the definition of odds is that the odds are equal to the probability P divided by 1 minus P. And, you may have encountered odds anywhere, in your travelings through the world, like if you've ever gambled or played cards or something like that. Not necessarily D&D at Las Vegas, but this is how odds are calculated officially. And this is going to be, well, number one, a little bit confusing, but it's also going to be sort of crucial to what we're going to talk about with logistic regression because those models are based on odds ratios. So this, like I said, can be a little confusing because we normally think about odds and probability kind of synonymously, I would say, but they're not quite the same thing as you can see from this equation. So normally this is a question I would ask in class, but what are the odds of drawing a club out of a full deck of cards? So, there's 4 different suits in a deck of cards, going back to the Las Vegas and whatnot. And so if your probability of drawing a club is 1 out of 4, right? Because they're evenly distributed in that deck of cards. But the odds would be 1 out of 3. So the P is 0.25. The 1 minus P for that reason is 0.75. So 1 out of 4 on top and 3 out of 4 on the bottom. That gives you 1 out of 3 for your odds of drawing a club. Or maybe I guess you could say 3 and 1, something like that. 3 to 1. Yeah, that's a better way of saying it, which is actually how odds are normally expressed. So maybe I'll put that on the slide here. 3 to 1 is the way we'd normally talk about it. But that kind of gives away the answer to this next question as well. But what are the odds of rolling a 6 on a regular die, a D6? And if you haven't seen the answer already, it's 1 over 5, or in that case, it would be 5 to 1, right? So there are 5 chances that you would roll something other than a 6 on a die, and there's 1 chance that you'd roll a 6. So it's 1 to 5 is basically the ratio there. Okay, so right, this is how odds work. We can look through a few other examples. So for instance, we've talked about, the probability of getting a type 1 error. We set up our hypothesis, our null hypothesis significance testing paradigm in a way such that alpha equals 0.05. We only want to make a false alarm error 1 out of 20 times when we're running a significance test like that. But that basically means that the odds of getting a false alarm are like 1 to 19. So 1 out of 20 for the good guys and 19 out of 20 for the bad guys on the bottom. I think I'm going to have to get some new water, but just hold on a second. I'll walk you through the rest of this slide at least. So the odds of a type 2 error if beta equals 0.2, that would wind up being 1 to 4. What are the odds of the Minnesota Vikings ever winning the Super Bowl? It's a Sunday. They're playing football right now. I think they're beating the Lions, which are the worst team in the league, but that's about the only team they can beat. So that's not good. We're not going to talk about that, but hopefully that'll happen sometime before I pass away. But if it doesn't, whatever. At least I got to watch some football sometimes on Sunday afternoons. Anyways, the easiest way to think about this is to consider the relative proportions of a distribution. There are 2 sides to every coin, right? So let's think of, this is a normal distribution that's kind of cut off on the edges, but this is going from 0 to 10. This is the kind of normal distribution that we started out with way back at the beginning of this class, except I've shaded it in such that it has 2 sides. So there's side A right here in white, and then side B in gray. And side B is a little bit bigger. It takes up more of the distribution than side A does. So the odds measure will basically answer the question, what are the relative sizes of A and B? And I'm just eyeballing it. I'm saying, well, B is a little bit bigger than A, right? I actually plotted this out so that B goes from 4 on up and A goes from 0 to 4. That tells you kind of what X values that it, transpires, or I don't know what X values it takes up on either side, but it doesn't tell you what proportion necessarily of the distribution is in A versus B. We have to kind of do a little bit more math to calculate that. Right, but that's the answer we're basically trying to get at is the proportional answer. What are the relative sizes of these two sides of the distribution? I'm going to pause for a second and be back in a minute. All right, sorry about that. I'm back. I have a glass of water that doesn't taste like paint thinner. So who knows? Maybe I will survive and live to see the Vikings win a Super Bowl yet. But we're not talking about the Super Bowl today. We're talking about odds. So just in case you're curious, I put the code for how to plot this sort of graph in R at the bottom of the slide where we left off last time. It involves using a function or a sort of package called ggplot, which is super useful, super powerful as well. It can plot all sorts of fancy things in R, so you can check that out if you'd like to, but we don't have time to dig into that right now, unfortunately, because we need to figure out how we're going to use this concept of the relative sizes of A and B to our advantage in just analyzing statistics. So what we're going to do, first of all, is we're going to convert this a little bit. We're not going to use just odds by themselves. We're going to use what's called the Logit function or the log odds function. So to calculate this measure, you just take the natural log of the odds function. So we started off with p over 1 minus p, that's the odds. And the Logit function just takes the natural log of this, which is normally written ln with whatever you're taking the natural log of in parentheses. And we don't have a lot of time to talk about exactly what logarithms mean. I think we've mentioned it before in this class at some point. But this is the log to the base e. And so this is how the function is defined, even though the command for it in R is log. And even though both textbooks refer to it as the log without any other sort of specification of what its base is, because what's the natural log is how we normally think of it. So it's kind of, I guess, for some people, the default log, even though you might think of the default log as maybe log to the base 10 or something like that. And then, usually there's some people who ask, like, what is E? Just as a reminder, this is a constant. It's the number 2.71828, so on and so forth. It never ends. It's an irrational number. If hopefully you remember that, but it's not super crucial, but it's about 2.7 is its value. And it's kind of funny. Well, maybe more for me than for you, but I'm going to tell you the story anyways, because I, in addition to liking football and baseball and so on and so forth, I play ultimate frisbee competitively when I'm not doing linguistics or statistics. And I have a friend well, first of all, I guess ultimate frisbee is a pretty geeky sport. There's lots of engineers involved with it. And one of my friends, his name is Andrew Pickup. He was geeky enough to make his jersey number E when he plays competitive frisbee out in the world. I told him at some point that I liked that fact because it was kind of fun. And I was like, I always have trouble kind of explaining, what this value means to my students. And he's like, oh, you can just tell them it's the limit as n goes to infinity of 1 plus 1 over n to the nth power. And I'm like, okay, Andrew, I'll do that. And here I am doing that. So if you don't want to think of E as 2.71828, so on and so forth, you can think of it as this function. Limit of n to infinity as 1 plus 1 over n goes to the nth power. Yeah, right. If you actually, it's kind of funny because, I have to put these slides together before I actually present them to you. And what I've done over this past semester is work to get everything in sort of Microsoft equation format for these slides, which takes a little bit of work. And I was like, man, I don't even know how to do limits in the equation editor. And I thought it would take a little bit of time to figure out how to do that. But I'll show you if you go to insert an equation somewhere in your PowerPoint slide. And look over here, there's a limit feature. So this is anytime you want to put an equation that has a limit in it, you just go to this menu, and then lo and behold, it has common functions right here. The limit as n goes to infinity of 1 plus 1 over n to the nth power. So my problem was solved instantly, and maybe Andrew Pickup had a point. But you don't need to worry about this. You don't even need to worry about what a limit is for this class. You just need to know that we're going to take logarithms to this base when we calculate this log odds measure. Okay, why are we doing this other than to tell hilarious stories about sports? The log odds measure is useful for dealing with the odds proportions we get in the tails of a distribution. So just to remind ourselves, this is, what a normal distribution would look like if we split it into two parts, and we're trying to figure out, what are the relative sort of weightings of each part. And by tails, I mean what happens kind of on the parts of this distribution that got cut off, sort of way out here on the ends of the normal distribution as it floats down to zero. Yes, the limit is zero. But, one half of this will become very big if you draw the line like over here, and the other half will be very small, right? Or if you're way out on this tail, the other half will be very big and the other half will be very small. So what happens is that small changes in probability in those tails can lead to very large changes in odds. So we talked about, if our alpha is set to 0.05, what are the odds of getting a false alarm in our significance testing paradigm? And I said it's 1/19. If we set alpha to 0.01, then all of a sudden the odds become 1 out of 99, which seems like a pretty dramatic change. So like we're kind of just moving on the x-axis from 0.05 to 0.01, but the odds ratio becomes much smaller when we do that. So the log odds ratio kind of smooths out these extreme edges of a distribution. And so you just take the natural log of these ratios here, 1 out of 19 or 1/99, and that converts that number to the first one to negative 2.04 and the second one to negative 4.595. So roughly speaking, this number is going to be about twice that number rather than whatever this is, like 5 times as small, because we're kind of dividing this by 5, as it were. So it's not going to make quite as dramatic a change when we get out to those tails, so that it won't like totally skew the analysis at the end of the day if we were just trying to figure out how to calculate odds ratios on their own. So instead of trying to sort of make a prediction for odds ratios, we're going to use log odds ratios, and those are going to be our dependent measures in a logistic regression model. Wait, sorry, I'm going to pick back up again. I left off at the end of this slide, and then things went haywire afterwards. So I want to walk you through the derivation of the inverse of the log odds function, and hopefully not screw it up this time. But let's start off with y equals the natural log of p over 1 minus p. So this is just the log odds function over here, and I'm using y here on the left-hand side because, like I just said, y is going to be the dependent measure in our logistic regression model. So whereas before we're seeing how like y depended on x, normally in sort of some linear fashion, like slope times x plus intercept equals y. In this case, we're going to look at y not just as a raw value, but as one of these log odds functions. And then on the right-hand side, we're still going to see what looks like a linear equation, but this value will just be this sort of logarithm of this ratio. So with that in mind, maybe we can unpack p from this equation to get a sense of how p can have an effect on y, or vice versa, because we're used to kind of thinking about p or just a raw probability without this sort of extra apparatus of a ratio and then a logarithm on top of it. So if y equals the natural log of p over 1 minus p, you can unpack what's inside the brackets here on the logarithm side in this fashion. So maybe you remember this from when you learned logarithms, or if you don't, but it's basically the base of the logarithm to this power equals what's inside the parentheses. So e to the y power equals p over 1 minus p, because the base of this logarithm is the number e. So now we're at this point, and what we want to do is solve for p. So let's multiply both sides of this equation by the denominator over here, and then we get 1 minus p times e to the y equals p. Multiplying this in the denominator by 1 minus p cancels it out, so we just get p on this side. Now we're getting closer, but we just want p on one side of this equation only. So let's multiply these two things together. We get e to the y minus p times e to the y equals p. Now I've got p in this term. We could just move that on over to the right-hand side by adding it to both sides of the equation. We get e to the y equals p plus p times e to the y. And now just to isolate p, we can factor it out of this right-hand side. We get e to the y equals p times 1 plus e to the y. And to finally solve for p, we'll divide both sides of the equation by 1 plus e to the y. And we get the probability p equals e to the y power divided by 1 plus e to the y power. So when we have this sort of setup, that's what p is going to be equal to, basically. what does that mean exactly? Well, if y equals 0, that might be a good starting point, then p is going to be e to the 0 power divided by 1 plus e to the 0 power. And so if you take anything to the 0 power, it just winds up being 1. So that basically converts this whole thing to 1 over 1 plus 1, which is 1/2 or 0.5, right? So that's a pretty even probability. If you're talking about two possible outcomes, this is right down the middle, right? So you should, like when you flip a coin, you should get heads or tails with a probability of 0.5. And that's the sort of scenario we're talking about. When you do have a probability of 0.5, then y, your log odds ratio, is going to be 0. So that's kind of a landmark you can rely on. Here's another coin joke, right? Right, we're in the log odds ratio, we're basically comparing the relative sizes of A and B, at least that's the ratio part of it. And when we have this probability equals 5 situation, we're splitting the distribution right down the middle. So A and B would be equally sized in that case. And when they're equally sized, then the log odds ratio is 0. You get positive numbers when you have the bigger side of the ratio on top of the fraction in the logarithm part of the equation. And you get a negative number when the smaller part of the distribution is on the top of that ratio. So you could also maybe think of this with a couple of other landmark cases. I'll just walk you through a couple notes here about the value of the Logit function is the power we'd raise e to in order to get the normal odds value. Yeah, I don't know if that helps explain it or not, but just have this note here. Again, this is nice because it means the values of the function are symmetric around 0, negative, and positive. So let's walk through a couple more landmarks. We talked about that one. Another reference point is when, say, the value is 1 or negative 1. I have a note there, but if you think about it in terms of this equation, let's say our logit value y is equal to 1, then we get p equals e to the first power divided by 1 plus e to the first power. So we said e is about 2.7, so e to the 1 power is just e, right? So we get 2.7 divided by 1 plus 2.7, so it's basically 2.7 divided by 3.7. It's about 3/4, more or less. And you can kind of think about that again as that sort of odds ratio of like sort of a 3-to-1 sort of option there. And basically they can convert that to say one outcome is about 3 times more likely than the other, or to be more specific with E, that means the outcome is 2.7 times more likely than the other. So when logit equals 0, it's right down the middle. You get equal sort of probability of either outcome. When you get to 1, then one outcome is about 3 times more likely than the other, or E times more likely than the other, I guess you could say. So that can help you basically understand what this function is trying to tell you. I will also say the function itself breaks down at p equals 0 or p equals 1. It becomes undefined at that point. Not so much because of that y. Like the logarithm of 0 over 1, you're not going to get anything out of that. Or 1 divided by 0 is just as bad. It kind of goes out infinitely on either side. And that's kind of its value, is that, these tails never totally get to 0 or 1. You always have to have at least 2 sides of the distribution. It can't be all one or the other, which is what you would have when p equals 0 or p equals 1. So the reason this matters, like I said, we're going to use the log odds ratio as our dependent measure in logistic regression. And this is going to be appropriate for a lot of kind of results that you do get in linguistics experiments, such as if you're, trying to determine, or if you're asking people, is this sentence grammatical or not? If you ask them to identify what sound this is, maybe they get it right, maybe they don't. You could have, numbers like 7 out of 10 in some test of some sort. And that would count as proportion data, which we've seen before. And we're going to analyze, and we've learned how to analyze it before with like chi-square tests or proportion tests. We're going to use logistic regression here because with logistic regression, you can get sort of an analysis of more than one factor, how more than one factor contributes to the proportions that we're seeing. So in addition, we can't really use ANOVAs for this stuff because, proportion distributions violate our underlying ANOVA assumptions. This used to be, well, I guess I would say it used to be pretty common for people to just apply ANOVAs like across the board. And then they would kind of try to come up with this thing called the Arc Sine Transformation to deal with the fact that, there are these limits on, how, like, that you might get for a test, which is like flipping a coin 10 times. You couldn't actually go past like the 0 or, probability of 1 point in those scenarios. But they would try to make it work either way. It still doesn't make sense because you have problems like the errors are not normally distributed in sort of these proportion results. The variances are not necessarily equal across proportions, et cetera, et cetera. We've talked about the underlying assumptions for ANOVA. Many of them don't apply in these scenarios. So you can't just say, oh, I've got my results and their percentages, and I'll just apply an ANOVA to it. It's better to use logistic regressions instead because it's sort of the model that's built for exactly that kind of data. And it's not too hard to use these. It just involves a little bit of different kind of thinking about what goes into sort of the dependent measure. So the model will look like this. I mentioned this before. This is our Y. This is our dependent measure. It's this log odds ratio. And then the model side of it looks like basically what we've seen before. We've got A plus B times X, B being the slope here, A being the intercept of what would normally be like a linear regression model, except on this side we've got, a ratio or a logarithm of a ratio. So what it's trying to predict, the y side of this equation is no longer going to be a linear thing. It's going to be a ratio that has limits on either side, 0 and 1 in terms of p, right? And hopefully you never get to either side. So that's kind of setup that we're working with here. And when you have that sort of proportion data, hopefully you will start to immediately think that I need to apply this sort of model instead of ANOVA or just a general linear model instead. So let's play around with this as a means of analyzing David Durian's dissertation data. And this is an example from the textbook, which is pretty cool. And I will walk you through how it works by first loading up this data and actually maybe showing it to you as well. So I borrowed this directly from the textbook. Yeah, let's see how the Vikings are doing by it. Let's see, look, I made that joke about the Vikings. They're losing to the Lions. Worst team in the league. Anyways, here we go. You've heard me talk about baseball so much. Now it's football. It's like, when will this ever end? I don't know. Let's talk about Walmart. Let's talk about Columbus, Ohio. Also a big football town because that's where David Durian was when he was doing this work. So this is what the data look like. And at this point, it probably doesn't mean a whole lot to you other than the fact that you can see like things like stores that you might know, like Sparrow or Walmart. I don't think you know Meijer. They don't exist up here in Canada. Or Easton, Polaris City Center. These are the names of malls in Columbus, Ohio. What was David Durian doing in malls? Let me first attach his variable names to our R console, and then I'll walk you through that. So what he was doing was he was analyzing what sociolinguistic variables might be behind the trend of STRA, often being pronounced as STRA in American English. And I think he was doing this maybe about 15 years ago or so. I don't know the exact date. So this is sort of a tendency I noticed before I left the U.S. I left the U.S. in 2007, and I think this trend was first brought to my attention about 20 years ago, about 2001. So he was kind of getting some data on this as it was first starting to take off. It's still kind of a variable process, but sometimes when people say STRA in American English, and sometimes in Canadian English now too, they will say STRA instead. So those of you who have taken my 341 class have seen this clip before, but we might as well watch it again because why not? It's kind of funny. This is from the TV show 30 Rock. And I picked this up maybe about 15 years ago. I played it many times throughout the years, but now I'm going to watch it. And I'm going to see Alec Baldwin, and I'm just going to think, you shot somebody. Anyways, let's not be depressive. Let's have a laugh.
How was your evening with Thomas?
You mean Gretchen Thomas, the brilliant plastics engineer / lesbian?
What made you think I was gay?
Your shoes.
Well, I'm straight.
Those shoes are definitely bi-curious.
Regardless, I am straight. 100% completely straight.
All right, so again, ignoring the Alec Baldwin factor, let's focus on the stra sequence we get here, which is at the beginning of the word straight. And she says it 3 times and goes back and forth between pronunciations.
Gay.
Your shoes.
Well, I'm straight.
Straight with the sh option there.
Those shoes are definitely bi-curious.
Regardless, I am straight.
Straight with the s option.
100% completely straight.
Straight at the end. And the last bit is nice because she's sort of emphasizing it, trying to make it super clear. And even though she's trying to make it super clear,
% completely straight.
she says it in sort of the non-canonical fashion, right? With the sh there. Okay, so that's fun. And maybe you've picked up on this as well if you've taken a sociolinguistics class, but David's study was a replication of the famous Leboeuf fourth floor study from the early 1960s. And usually I ask people in class if they know that one, but you're not present here, so I'll just tell you about it briefly. Leboeuf in the early 60s was kind of the pioneer of sociolinguistics, and he did this sort of like man on the street, sort of data collection method where, and he wasn't on the street, he was in shopping malls, like places like Macy's or Saks, and I think the other one was Klein's, which must be like a local regional sort of shopping center in New York City, which is where he was doing this research because he was interested in the sort of New York City variant of fourth floor, where they drop their R's in a non-rhotic variety of English, right? So he would just go find something in Macy's that was on the 4th floor and then ask one of the people working at the store where that thing was. And they'd say, it's on the 4th floor. And then he'd just start writing in his notebook if they said the R or not in 4th floor. And then he would always ask it twice as well, too. So he'd say, where did you say? And say 4th floor, with the idea being that if they were emphasizing it, they might sort of shift to a more formal pronunciation, or at least a more emphatic pronunciation, whatever that might entail. So maybe if they're trying to sound more like standard English, they might pronounce the R more in that case, or maybe they would go the opposite way, whatever they happen to be thinking. So David did this as well, but it was the 2000s, so he didn't have just malls in New York City to work with. He was actually he went to malls in Columbus, Ohio, and asked people where a certain street was, and then he counted their stra versus stra responses. And again, kind of doing it like guerrilla linguistics style, where he just wrote down their responses with on-the-fly transcriptions, so we kind of have to take his word for it. So he asked for the street name twice, getting both the casual sort of initial and the emphatic productions, where he pretended like he didn't understand, so they didn't say it again, hopefully clearly. Got 240 tokens in all, balanced for male and female speakers, and then he got a variety of other social and class factors, which we can ignore for this exercise, like, just to like close the circle, like Walmart, I guess, is probably like the working class sort of option, and Sears might have been the like middle class option. I don't know. I haven't gone through the whole story. It looks like there's a lot of sort of interesting little places. Is Gap the fancy one? I don't know. Maybe. Polaris. I think Polaris was kind of fancier in Columbus when I was there. Either way, we don't have to worry about that for our purposes. But the data is organized with one observation per line. And then he's basically counting how many times to say stra or stra. And this is something, so this is the first variable here, whether it's a stra production or a stra production. And up until this year, I've been able to just use this field as the dependent measure in a logistic regression analysis, but for some reason that changed this year in R's new package. So we can't use that, but luckily for us, we have these stra numbers here. So 1 means a stra production and 0 means a stra production. So this is the one that's sort of the change. And then there's also data here on whether it's the casual, which is less, or the more, which is the emphatic production. And then we'll also look at gender, whether it's male or female production. And then we'll just kind of leave it there. Right. So he had to get a lot of this information like age and so on and so forth, I guess just by guessing, because he wasn't interviewing these people or getting official sort of data. He's doing it, like I said, guerrilla style. But either way, our dependent measure is whether this said stra, which is a 0, or stra, which is a 1. And so what we're going to do is that we are again going to compare the proportions of hits and misses in the Logit function. So the proportion of stra productions and the proportion of stra productions. And maybe if you want to think of hit, like the stra as a hit because like something new is going on there, that's fine. And actually that is something I should have mentioned when I was talking about Tina Fey. So that clip, like I said, was from sometime in the 2000s decade, whatever you call it, whether it's the oddies or the naughties or the whatever 2000s. Tina Fey is a woman, it turns out, and this is a change in progress, or it's a change that's spreading to some extent, at least at that time. And women, especially young women, tend to be at the forefront of these changes, right? So you'd be more likely to hear it in the speech of somebody like Tina Fey or maybe an even younger female. Anyways, sorry, I went on a digression there. I didn't want to go on. But anyways, we might expect there to be gender differences in how often this variant appears in the speech of these speakers in Columbus, Ohio. But ultimately, in terms of how we're going to construct the model, we're going to compare proportions of stra to stra productions and I want to focus here on the proportion part of this. So proportions of hits and misses, not some percentage of hits versus some overall total. So we can look at this more closely. I'll show you kind of how you get the data that we need. Because I'm just going to, at the end of the day, we're going to be able to, just kind of crank out one command and it'll spit out a bunch of numbers at us. And I want to show you at least a bit of where these numbers come from. So we'll look at sort of this emphasis factor first. So will people be using the stra variant more often when they're sort of emphasizing or trying to make their speech clear? The second production, and we can compare that to sort of the less or the more casual option. So it's just looking at how often we get the stras in the more emphatic context. There's 14 of them out of 120 there, because we have 240 total. We're going to split it in half, so there'll be 120 total. And then this is the less context. We get 43 out of 120 there. So it looks like on the surface, at least, they're doing it more often in the less formal context or the more casual context. But the point is, we're not comparing 14 to 43 here. Instead, we're comparing the ratio of stra to stra in the two conditions, which is why I went through this whole business at the beginning of this lecture about these odds ratios, right? That's kind of the foundation of how the logistic regression model works. It's not percentages, it's not the P's, it's the odds, it's the ratio instead. Okay, I think I've talked about that enough. Let's just take a look at how this model actually works. It might be easier to think of this in tabular form. Actually, yeah, I haven't talked about this enough because this will make it hopefully totally clear. But like I said, there's 240 total productions. We get half of them in the less formal context and more half of them in the more formal or the more emphatic context. So we get 43 stras for the less group and 14 stras for the more group. What we're comparing here are these two log odds ratios. So we're comparing the natural log of 43 over 77 to the natural log of 14 over 106. Yeah, and I've got a variety of different ways of sort of describing the two parts of the ratio that we're comparing. So P versus 1 versus P, or hits versus failures, stras to stras, changes versus no changes, so on and so forth. But it's this ratio that's the important part, not 43 divided by 120 or 14 divided by 120. It's 43 divided by 77 or 14 divided by 106 that matters. Okay, so to make these comparisons, we use the GLM function in R rather than the LM function. And I think I told you a long time ago, the LM stands for linear model. And the GLM is going to stand for generalized linear model. Take that for what it's worth. So the actual command looks like this. So we can do this relatively easily with the R command at our disposal. So this, I walked through the whole log odds ratio stuff at great length, and it turns out that when we actually run the command, it's a lot simpler than that, thankfully. But the numbers we're going to see as a result of running this command will be based on that log odds ratio. But just to set up the model itself, you take those STR numbers, which are a 1 or a 0, if you remember, up here, this column right here. And that's your dependent measure. And then this is the model. You say, well, does it depend on the emphatic factor or not? So does it depend on that? The family equals binomial is how it gets converted into a log odds ratio. And this just specifies the data set we're using. And then the GLM runs the analysis for us. So that's relatively straightforward. This is one case where R makes it easy. If we pump out the results, we get something that looks like this. So there's a lot of stuff in here that looks familiar, including, I guess I'll just quickly mention the AIC factor, which we're not going to dwell on here. But the part of this that we care about is these coefficients. So this looks like the old linear regression models that we played around with a while back, including having an intercept. And where we normally expect kind of the slope for a factor, we get that here. So we have an estimate of negative 0.58 for the intercept and what looks like an estimate of negative 1.44 for whatever the slope happens to be. There are p-values for these guys as well. They're both starred as being significant. Let's not worry about that too much. For now, we'll just say the intercept is our base model in this particular case. And I'll point out, I think I pointed this out before, but it's worth repeating, that R is goofy. It just walks through the factor levels in alphabetical order. So remember our independent factor here is emphatic, which has two different levels. It has less and more. So guess what? Less comes before more in the alphabet. So less is the default value for that variable, and it just compares the more numbers to that. So the intercept is the logit value of the less as opposed to the more cases. And that means it's the log of 43 divided by 77. Just to make that super clear, I'll type that in here. The log of 43 over 77 is this number right here. That's our intercept estimate. It's not hard to calculate that. It was much more complicated when we weren't calculating those best fit lines. Remember those? Hope you do. But where those numbers come from is just this to that, right? So we're only looking at the less part of the table for now. It's just this ratio. And that the log odds ratio of that is negative 0.58. So because the smaller number is in the numerator there, we're getting a negative number overall. And you can kind of see that maybe this is not quite twice as big as that. So we're getting a negative 0.5/8. Remember, if I said if you're at -1 for your log odds ratio, then this here should be 2.7 times bigger than that, more or less. Okay, what does this other number mean though? This estimate. Where do we get that? It's actually quite simple in its own right. The emphatic slope is just the difference between the log odds function for both groups of observations. So we take the logit value for the more data, subtract from it the logit value for the less data, and we get this number negative 1.4418. So the reason we're getting that is because the log odds ratio for more is 14, is the log of 14 divided by 106. So that's a more negative number. It's -2 and change. And just so you can see where the overall value comes from, if I subtract from that the log odds ratio for the less data, I get a negative 1.44. Yeah, which is what we get here, more or less, right? So that is where this number comes from. And it's that easy to calculate. The rest of this is more complicated, and I am not going to walk you through it. As I mentioned here, there's standard error estimates for these intercepts, but I don't know how they're calculated explicitly. We're not going to worry about that for now. We'll just take the resultant p-values anyways, because we can trust R to do its job. And this will give us a sense of what factors are significant and that we should keep in our logistic regression model, basically. But to tie it back in with our original equation, y, which is basically the odds, or the log odds of getting a STRA response, is equal to a plus bx, where you get a as negative 0.5826 plus b, which is negative 1.4418 times x. And yeah, so in this case, remember, just because of the way R sets up the model, 1 is the more option, and where x equals 1 is the more option, and x equals 0 is the less option. So when x equals 1, we add this factor into the calculation of y, and that basically means, because it's negative, that means you're going to get fewer STRA productions, right? You're going down in terms of your overall ratio, which I think is hopefully pretty clear. 14 over 106 is a smaller number than 43 over 77, right? Basically how to interpret this is that when people get more emphatic or more potentially formal, they produce that STRA variant less than the STRA variant, than they would in the casual sort of scenario. Okay, hopefully that makes sense. We're stumbling through this, but we'll make it. Because, like I said, once you get the hang of it, it's actually not as complicated as a lot of the linear regression models. What I want to look at next, though, is this potential gender factor, right? So I said oftentimes young women can be leading the way on these changes. Is that the case for the STRA production, at least in Columbus, Ohio? Well, we can run that pretty simply. Maybe I'll move this up a bit so you can see it better. So we're looking at the STR numbers as our dependent measure, and then gender alone as our independent factor. And if we run that, it looks like we get a significant result where gender does make a difference here. Where do these numbers come from? I'm not going to walk through all the math again. I'll just say this is significant as a factor. And I'll show you the table, which has not only the less and more factor in it, but also the gender factor in it. And we kind of have to sort of generalize a bit over both of these factors to see the gender factor by itself. But this is men and women. And again, we're comparing proportions here. But basically, it looks like on the surface that we're getting more STRA variance from the women than from the men. This number, at least, is on the surface bigger than that, and this ratio is bigger than that as well. It's the same sort of balance, more or less, in the more emphatic context, where you get 12 STRAs and 48 STRAs for the women, and just 2 STRAs for the men, and 58 STRAs for the men for the more emphatic context. So it looks like the overall balance is the same, and women are just producing more STRAs than men in general, and we can kind of confirm that with this model, right? So in this case, the intercept value, this negative 1.67, is going to be the sort of overall log odds ratio for the men, because M comes before W in the alphabet, right? So it's relatively negative. It's more negative than it was before, which is negative 0.5826. And then when we add the women factor in it, that basically is saying that women produce more STRAs than the men, because this is a positive number, and this p-value being small and stars being here just means that this is significant. It makes a significant difference what the gender of the speaker is. Right. So I've got a little note here. This is where the numbers come from. This is something that I used to do explicitly in class. Just walk through the building of this table. We don't have time for that now, so we'll just move on. But this is I wanted to split it up in this way because I wanted to see if there's potentially an interaction. So we've run 2 different logistic regressions on this. We've got one significant effect for the emphasis factor, and then we've got another significant effect for gender, but we've run them separately, so we don't know how they might affect each other or how they might interact. Is there a significant interaction? It kind of looks, just based on this data, like maybe not. We get kind of the same overall balance shift between men and women for both less and more context, but you never know. Let's run the numbers and see what they say. So, do these factors interact with each other? This is how you run the logistic regression to find out. Again, this is basically what you would do, like what we did for ANOVAs before. Sorry for flipping back and forth constantly like this. But we've got our 2 factors, emphatic and gender, and then we're just looking at the interaction like this. So let's run it. See what happens. And we get this. So again, we get a new intercept estimate here. And then we're getting new slope estimates for both the emphatic factor and also the gender factor, and then one for the interaction as well. It turns out if you look over here, we only get one significant result, which is the emphatic factor, and the gender is close in terms of its p-value, but no cigar. We just get a little period, a little dot. So, right, how do we get these numbers? For this analysis, we get these as our slope values, or I've got, the intercept first here, so sorry for getting ahead of myself, but the negative 0.928 number here is when you have the first levels of both factors in terms of where they are in the alphabet. So the word men comes before women in the alphabet. The word less comes before more in the alphabet. Our default intercept value is just the ratio for men in the less context. So it's the 17 divided by 43 here. And just to confirm that, again, I'll show you log of 17 over 43 negative 0.928. It's this. Okay, that's where we start from. It gets a little more complicated when we start calculating these interactions. For the emphatic factor, you take the you make the shift for the men first. So you keep the men part of it constant, and then you shift from the less to more emphatic context, and you wind up comparing this ratio to this ratio alone, and we'll call that the more factor, but what that winds up being is negative 2.4393. This is a very small ratio, right? 2 out of 58. Okay, so that basically makes the number of STRA productions go down a lot. That's why it's a big negative number. And then we can independently see what happens when we add the women factor to it. So in this case, we're again starting from this baseline of the men and less, and then we compare that to the women and less context, where we have 26 productions of STRA compared to 34 productions of STRA. That winds up being a positive number because we're getting more STRAs. So that would be this compared to this by itself. How do we get this number? We've gone two different directions with both of our factors. This gets a little more complicated. So it's actually complicated to the point where I've tried to color code it. But what we start out with, this is our baseline. And this is kind of where we wind up, which is where both factors are different. So our baseline is men and in the less context. And we want to be able to compare that to the women and more context, which is where we have 12 STRAs and 48 STRAs produced. But in between those, we have to account for both our more factor and our women factor. So from this, we subtract the more factor, which I have in blue, and then we also subtract the women factor, which I have in purple. And at the end of the day, we also subtract the baseline, which is men and less. That's a lot to work through. But what we wind up getting out of that is just this value 1.3213. The p-value for this is, not that far off from 0.05. It's not significant, but you can see it's a fairly healthy effect size on top of everything else. Because we're getting, it looks like, more STRA productions here. That's basically what the positive number says here, and it's basically twice as big as what we get for the gender factor, which is also not significant. So if we just run this on its own, we see a significant effect for the context, the emphatic context, or the first versus second repetition. We don't get a significant effect for either the gender factor or for the interaction, though. Okay, just to kind of go back to the conceptual part of this, with each of these factors, we're just seeing how much it contributes to the Logit values in comparison to a simpler model. And this is just like what we were doing when we were adding multiple factors to a linear regression model. Remember, we did that sort of stepwise process where we're adding like, oh, does familiarity make a difference in terms of reaction time? Oh, yes, it does. Well, let's see if we add frequency on top of it, if that will make a difference in terms of reaction time as well. Okay, actually, in addition to sort of this looking like a multiple regression model is actually a little more like a two-way analysis of variance, where we have this baseline mean. In our example, that was where the men in less context. And then we have two independent factors added to it, either the emphasis factor or the gender factor, and then also an interaction factor at the end. We're not thinking so much about the residual variance that's left over there, but that's basically how this model is structured. So even though, our dependent measure is structured in a different way, the overall model kind of is built up in a similar fashion. We're just building on all these tools that we're acquiring throughout the semester, right? There's a reason I'm telling you about all this stuff. And point number 2 is the order in which you add factors can have an effect on their significance. We'll see that in the last bit here, where we talk about the analysis of deviance. But point number 3 is that some of these factors we'll want to keep, while others we can just discard. Like I think I hopefully made clear when we're talking about ANOVAs and also multiple regressions, is that you can make choices about what to include in your model and what to leave out. And that's true with logistic regression as well. It's the same model building principle across the board. Even though this is similar to an analysis of variance, we can't run an ANOVA on this stuff for the reasons I mentioned above, so I'm not going to dwell on that any further, but it's just because of the way the dependent measure is structured, that matters more than anything else in terms of what kind of analysis we can use for this stuff. I mentioned this a second ago, but instead of running an analysis of variance, we can run what's called an analysis of deviance, which to me sounds a bit like some sort of weird French postmodern philosophy. So we're not going to go there. It's not that kind of deviance. It's more about how our observed data deviates from what you might expect out of a model of the data. So this, I'll show you how to do this in R. It's relatively straightforward in terms of the commands. Figuring out what it means takes a little more time. This is basically a chi-squared test, but we're using a different metric. Instead of chi squared, we're using g squared. So the g stands for, of all things, goodness of fit. And there's an equation for it in this textbook, but it's slightly wrong. So I'm going to give you the correct version of it, at least in terms of how R calculates it. But it's g squared equals 2 times the sum of O sub I, where O is observation sub I, times the natural log of observation sub I over expected value sub I. So this, again, will look a bit like in odds ratio. It's not quite the same thing, but it is taking the log of some ratio, basically the observed value over the expected value. The problem with the equation in the textbook is that there's no negative sign at the start. If you happen to carry it, just this is positive overall. So let's just see how this works. It's going to be basically like a chi-squared test because we're comparing the observed and expected values in a contingency table. And for this reason, it may be worthwhile to remind ourselves of what the chi-squared math looks like. That also involved observed and expected values, just the actual equation is different. So this is just observed divided by expected. This is sort of the squared difference between observed and expected divided by expected. And then in this case, you multiply it by the observed. Whatever, just that's the math, right? I can walk you through a basic example, but it's involving similar sort of variables as we go through either the g squared or the chi-squared example. I've got this note here about organizing your count data in terms of two distinct proportions, but R is basically going to do that for you because otherwise this sort of proportional analysis is not going to work. So let's go back to this David Durian Stra data. And this is the same table we've seen before, but here I'm going to show you what the probabilities are, or at least the observed probabilities are, in terms of how often we get these particular numbers in each cell of the table. So we started out with just these 4 numbers here in the upper left corner. So the way I'm getting these p-values is I'm just taking 43, the observed value divided by the total number. And like I said, for what we did before for logistic regression, that's not sort of the proportion you want to be comparing, but this is just how we're going to generate the expected table here. So 43 divided by 120 is 0.2375. 77 divided by 120 is this number. 14 divided by 120, so on and so forth. Actually, I'm misspeaking. So sorry, it's not 43 divided by 120. It's 57 divided by 240. I'm looking at the total values here because what we want to generate are these expected values for these four numbers. So we don't take them as givens. We take these total numbers as givens, and that's why at the bottom here we have p-values of 0.5 for both the less and the more numbers because, those were evenly split by design, but that's what they wind up being for the p-values when you kind of run this calculus. So this is 120 divided by 240 is 0.5. 183 divided by 240 is 0.7625. Sorry about that. It's a funny kind of day. Anyways, this translates into this contingency table. So like I said, to get the number we expect here, we take 240 times the probability of getting a less production times the probability of getting a straw production, the overall probability of a straw production. Because what we're trying to see is if there's any sort of kind of interaction going on here between the rows and columns. 240 times 0.2375 times 0.5 is equal to 28.5. And we get the same number here in the more column for hopefully obvious reasons because we're doing the exact same math. The straw row is going to have higher expected numbers because 0.7625 is about 3 times as big as 0.2375. So we get 91.5 for them. But our total numbers wind up being the same, right, for both the rows and the columns. But what we want to look at is how much these four numbers deviate from these four expected numbers. That's where the deviance comes from. Get your minds out of the gutter. All right. Anyways, at this point, we can take a look at what the chi-squared analysis would do. We've seen this before, and you start out with the observed minus expected. So like 43 minus 28.5 is 14.5. 14 minus 28.5 is negative 14.5, so on and so forth. You square all those guys, you get 210.25 in each cell. Remember, there's only 1 degree of freedom here because we have a 2 by 2 table. You divide those by the actual expected numbers. Things start getting a little more interesting. So you get 7.3 at the top, 2.3 on the bottom. You sum up all of those numbers and you wind up with an overall chi-squared statistic of 19.36. And then you just evaluate that in terms of the 1 degree of freedom that you have. The g-squared deviance is going to be calculated in a fairly similar way, but the important part is the important difference is where you start out from, right? So with the chi-squared statistic, it's observed minus expected. And then for the g-squared, it's observed divided by expected because you're looking at those proportions again, like a ratio. So just to make this hopefully clear, I'll compare it to what we had before. So we have this observed minus expected here. So for chi-squared, for this number, is 43 minus 28.5, which gave us 14.5. So that's minus. That's what's going on there. But what we're going to see for the g-squared deviance is a ratio. So it's 43 divided by 28.5, which is about 1.5 or 1.509 is what it turns out to be. And then likewise, for the more number there, it would be 14 divided by 28.5, which it might be easier to see that that's about half exactly. So that's 0.491 here. So you start out with those ratios, and then you take the log of those ratios, like we've seen before. If it's above 1, we're going to get a positive number down here. If it's below 1, then we get a negative number, so on and so forth. That's how the log odds ratio works. We then multiply those by the observed numbers. We get a lot of decimal point information over here. We don't need to worry about it so much because in the end, we sum it up and then multiply it by 2, and we get a g-squared statistic of 20.08, which is pretty close to what we got for the chi-squared statistic. We just got there in a different way. So this is 19.36. Yep. And then this is 20.08. Okay, so that's where this comes from, but maybe that's enough math because it's not all that super important. You need to know what's more important for your purposes is how to run this in R. Basically, it's going to look like what we saw before. This is the analysis of deviance again, but maybe I can expand this so you can see. No, not quite. It is basically this exact same command, except I'm adding this comma test equals chi-squared here, which gives us sort of the ANOVA or the analysis of deviance. And the other part that's different is we're going from summary, which will look like a linear regression summary, to the ANOVA part here. So it'll be more like an ANOVA set of results when I actually run it. It's a little bit different though. So here, just this number, 20.08, that's the G-squared statistic that we calculated here. What goes on beyond that is harder to calculate. It actually depends on what factors are already in the model, just like what we saw with the multiple regression analysis. So we don't have time or the need to walk through how these other deviance statistics are calculated, but this is sort of the analog to the F statistic that we got through analysis of variance. So we're seeing basically how big of an effect size this is. We convert that into a p-value, and we get a very small p-value for the emphasis factor. And in this analysis of deviance, we do get a significant effect of gender on top of that, because this p-value is less than 0.052 based on this deviance number here. It keeps getting smaller and smaller, though, as we add factors. That's kind of how deviance works, is you kind of want to be able to account for as much deviance as possible with the factors you include in the model. So you're including the factors that account for the most at the start, and then you get like smaller and smaller amounts of deviance at the end, which eventually means you don't have to keep adding factors to your model, because the smaller model will explain as much as is parsimonious to explain, I guess you could say. We've seen that principally before with Occam's razor, right? But the point is here, we get two significant factors, so we could include both of these in the model as significant. And this is how you just basically run this in the sort of analysis of variance way, except we're calling it now analysis of deviance. Okay, that's where those numbers come from. We can also try the same sort of analysis with the ABX data from Sue Jackson's work, which we've seen several times before. What we haven't looked at with this data set before is the correct numbers so much, or at least we have, but we can't really analyze those in a linear regression or ANOVA fashion. So remember, this was an ABX study where you were hearing two different stop types, A and B, and then you heard a third, X, and the job was to match X with either A or B. So X was one of the first two. You had to figure out which one it was. And then people got that question right about 75% of the time, but did their ability to make that sort of matching depend on, what was their native language, what kind of contrast they're listening to, and then what kind of voicing appeared in the stop itself. We walked through this data multiple times. We can just run through this quick and dirty analysis of deviance. Again, get your mind out of the gutter. It's not that kind of dirty. But we get significant effects here of contrast and context. And this is one case where we do get a significant interaction. You can see these are pretty large, healthy effect sizes all across the board, but there's a huge amount of data in this, so yeah, it's maybe not that surprising. It's a little tricky. I don't have time to walk you through a really comprehensive way to talk about like post-hoc testing for things like these factors here. I can show you kind of a simple way to do it, which is to go back to the summary command, and that'll give you a sense of what is sort of making a difference here. So we got significant effects for contrast, context, and then language by contrast. So with the contrast, remember there are three pairings of stimuli here: the BU, breathy unaspirated, HB, regular aspirated, breathy aspirated, and then HU. So the BU comes first in the alphabet for that again. So these numbers are basically going to compare to that default value. So HB is going to tell you a little bit about which this is significant because we have a star here, a p-value of less than 0.05. But this number is basically in comparison to the BU default. So when listeners are hearing the HB pairs, they're getting fewer correct responses than the BU pairs. And when they hear the HU pairs, they're getting more correct responses than the BU pairs, because this is also significant, and this is a positive valued number. So the BUs are somewhere in the middle. There's a significant effect of context as well. Those levels were L and an S, long voicing, no voicing, and short voicing. It looks like the only one that makes a difference there is the no voicing. They were getting more correct responses for that because this is a positive number and it's significant as well. The one that's kind of hard to interpret is an interaction like this. It should start out with language and contrast. That should start out with English and BU as the defaults there because English comes before Hindi and then BU comes before the other contrast types. But then you got to figure out, well, there's one, I think there's one significant level pairing for that interaction, which is Hindi and HU. So what that is basically saying, here's our default log odds ratio for the English speakers, and the Hindi speakers look like they're doing better. They get a positive addition to that. And then to interpret this, you also have to, so we're adding on the language Hindi so that we get this boost to that. And then we're making a special sort of adjustment for the HU stimuli, which is this adjustment. So overall, it looks like people do better with the HU contrast, but for the Hindi speakers and the HU contrast, they're doing worse for some reason. So that's the nature of the interaction there. So basically, I don't want to dwell on this too much, but it takes a little while. You kind of have to step through what all these things mean. But that's how an analysis of deviance would work. I'm just thinking sort of in phonetic terms again. So I think the reason behind this is that HU contrasts are typical in English, but not as typical in Hindi, where you have more breathy voiced aspiration. So that's probably why they're not doing as well with it, and that's where the language factor comes into play. Anyways, like I said, this is a 3-factor model, so it can get pretty complicated pretty quickly. Again, if you run ANOVAs like this or analysis of deviances like this, buyer beware, I guess you could say. It can be a little complicated to figure out what's going on at the end of the day, but that's how you can do it in R with this sort of logistic regression model. That's all I'm going to say about this for today. I think I've said enough. We're going to talk about something that's even more complicated for the bonus lectures at the end of the semester, so stay tuned for those if you so desire. Otherwise, we're done for the afternoon. Let's check in one last time. How are those Vikings doing? Oh, they're catching up. Maybe it'll be a good day. Oh, it's already a good day. It's sunny outside, so what am I worried about football for? All right, see you next time.